Welcome everyone. I'm thrilled you're here for Module 3-1, the molecular race. Today we are going to look at the molecular race. This isn't just a textbook definition of moving fluids. This is about how we, as analysts, control how chemicals behave under extreme pressure to get the data that everyone else misses. Think of me as your mentor in the lab today. We aren't just looking at colorful spots on paper anymore. We are looking at the physics of the race that allows us to detect substances at the atogram level. Let's get started. Have you ever noticed how your speed changes depending on the environment? If you're walking down an empty, polished hallway, you're hitting your top speed, no problem. There's nothing in your way. But now, imagine trying to cross a crowded shopping mall during a Black Friday sale. Suddenly, you're dodging strollers, you're getting distracted by window displays. You move slower. But here's the key. You didn't lose the ability to walk. Your physical capacity to move didn't change. What changed was the environment and how you interacted with it. In the world of analytical chemistry, we call this interference or interaction. Chromatography is simply the art of creating the Black Friday mall for some molecules while keeping the empty hallway for others. In our world, chromatography is the bouncer at the door of the mass spec club. It decides who gets in and when they get in. Before we dive into the race, let's look at our map. By the end of this module, you won't just know what chromatography is. You'll understand why it is the backbone of mass spectrometry. We are going to define our athletes, the analytes, and the track they run on. We are going to get comfortable with the math, specifically the partition coefficient, which is the rule of distribution that governs every separation in your column. Most importantly, we are going to connect this back to the pain points of MS, ion suppression, and coelution. If you've ever had a run fail because your signal was drowned out by noise, this module is your cure. We are going to learn how to use polarity and affinity to ensure every single molecule gets its own time slot in the detector. New students always ask me, if the mass spec is so powerful and sensitive, why do we even need the chromatography step? Why not just inject the raw sample? In mass spectrometry, we call this ion suppression. When everything hits the MS detector at the same time, what we call coelution. The big, loud molecules drown out the small, quiet ones, your targets. You get a messy signal, or worse, the detector is overwhelmed, and you see nothing at all. Chromatography makes the molecules line up and enter the MS one by one. It's the difference between a chaotic riot where no one is heard and an orderly parade where every participant is acknowledged. We use differential migration to turn that riot into a parade. Every race needs a track, athletes, and a driving force. In our chromatographic world, we have three main players that interact to create separation. To master the lab, you have to understand the personality of each. First, we have the analyte. That's our athlete, the specific substance we want to isolate from the mess. Second, we have the mobile phase. Think of this as a constant wind, or a river current, pushing our athletes forward. It's the moving fluid stream. Finally, there's the stationary phase. This is the track itself. But it's not a smooth track. It's more like a muddy path or a series of hurdles designed to hold the athletes back. Over the next few slides, we're going to look at each of these in detail, because if you can manipulate even one of them, you can change the outcome of the entire race. Let's talk about our athlete, the analyte. In your lab reports, you'll call this the solute. This is the component of the mixture we actually care about. What makes chromatography so versatile is that our athletes can range in size from the smallest molecule, such as hydrogen, to massive viruses composed of millions of atoms. The analyte's behavior is dictated by its affinity. It is constantly caught in a tug-of-war. Does it want to stay in the moving fluid, the mobile phase, or does it want to stick to the track, the stationary phase? Every species has a different personality or affinity based on its chemical structure. As an analyst, your job is to know your athlete. If you know how sticky your analyte is, you can predict how long it will stay on the track. Next is the mobile phase. Think of this as the driving force. It is a moving fluid stream, either a liquid or a gas, that carries the mixture through the medium. If you are using a liquid, you are doing liquid chromatography. If you use a gas, it's gas chromatography. In the lab, you'll often hear this called the eluent when it's entering the column. Its job is simple. Move the molecules forward. It provides the kinetic energy to keep the race going. However, the mobile phase isn't just a passive carrier. By changing the composition of this river, for example, by changing the solvent ratio in LC, you can make the water more or less attractive to your athletes. This is the first dial you turn when a separation isn't going your way. Finally, we have the stationary phase. If the mobile phase is the wind at your back, the stationary phase is the mud under your feet. It stays fixed in place, usually a porous solid matrix or a thin liquid layer adsorbed onto a solid support. Its entire job is to hold the athletes back. It acts as a constraint. Without this resistance, every molecule would fly through the system at the same speed, and you'd have zero separation. The magic happens because different molecules have different levels of attraction to this phase. Some molecules think the stationary phase is sticky, and they spend a lot of time hugging the track. Others find it repulsive and move on as fast as possible. This resistance is what transforms a mixture into a sequence. The race happens because of a concept called differential migration. Every single molecule in your sample is being pushed by the driving force of the mobile phase and held back by the resistive force of the stationary phase. But it's not a static process. Thanks to kinetic molecular motion, molecules are constantly being exchanged back and forth between the two phases. They aren't just sitting in one place, they are jumping in and out of the river. If a molecule's distribution favors the mobile phase, it spends more time migrating and moves away from the other species. The separation you see on your screen is simply the cumulative result of millions of these tiny jumps between phases. The analyst's power lies in manipulating these forces to widen the gap between those jumps. How does a molecule decide how fast to run? It comes down to two primary behaviors: adsorption and solubility. Adsorption is what I call the stickiness. It is the physical ability of the analyte to attach itself to the surface of the stationary phase. If an analyte has high adsorption, it's a track hugger. It's going to move slowly. Solubility, on the other hand, is the speed. It's how much the analyte likes to hang out in the mobile phase. High solubility means it wants to stay in the river and move fast. In the real world, the difference between a pro and an amateur is knowing how to balance these two. If your molecules are moving too fast and coming out all at once, co-eluting, you need to make the stationary phase stickier, increase adsorption, or the mobile phase weaker, decrease solubility. If you want to sound like a consultant in the lab, you need to talk about the partition coefficient, denoted as K. This is the rule of distribution. It's a ratio that describes exactly how a solute distributes itself between the two phases. Think of it as the ratio of time spent in the hotel, stationary phase, versus time spent on the road, mobile phase. If K is high, the molecule is a stayer. It prefers the stationary phase and will move slowly. If K is low, it's a goer. It prefers the mobile phase and will fly through the column. The winner of the race, the first one to hit the detector, is simply the molecule that spends the least amount of total time in the hotel. Mastering K is how you master retention time. I want to pause here for a pro tip. Why do we obsess over this value and these separation times? It's because the mass spec's ion source is like a very narrow doorway. If 1,000 molecules try to jump through that doorway at the same exact microsecond, they will crash into each other. Some will be suppressed and never make it to the detector. By using chromatography to separate them, to give each species its own unique time slot, we ensure the MS can see and quantify every single one accurately. Whether you're doing targeted quantification, suspect screening, or untargeted profiling, chromatography is what gives your data integrity. Without separation, your addigram sensitivity is useless, because it's buried under a mountain of matrix noise. How do we actually control that stickiness or K value? We use the fundamental principle of polarity. Like attracts like. If you have a polar analyte, it's going to have a high affinity for a polar stationary phase. They form a strong adhesion, which slows the analyte down. On the flip side, a non-polar analyte will feel out of place on a polar track. It will prefer to dissolve in a non-polar mobile phase and zip right through. By choosing the right stationary phase and the right mobile phase, you become the master of the race. You can slow down the fast runners and speed up the slow ones until they are perfectly separated. Let's wrap this up. Chromatography, it's about controlling equilibrium to create order out of chaos. Always remember the fundamental struggle. The mobile phase pushes and the stationary phase resists. The partition coefficient is the mathematical expression of that struggle. We do all of this so our mass spectrometer doesn't get overwhelmed by noise. In the field, chromatography is often 80% of the work and 20% of the glory. But if you master the physics of the race, that is what separates the amateurs from the experts. Knowing the rules of the race is one thing. Having the right shoes is another. In our next unit, Module 3-2, the separation tool belt, we are going to look at the hardware. We'll compare GC and LC and help you decide which tool to pull out of your belt for the job. You've mastered the race. Now it's time to master the equipment. I'll see you in the next module.